Welcome back, Pre-Calc. Our objective today is going to be to look at exponential models. Models are functions that help us make predictions or help analyze sort of real-world applications. So I've got the checklist on the screen. You know what to do from here. All right, so today we're going to be still needing these objectives of knowing how to solve log and exponential equations. So I've got a little warm-up. Go ahead. I'm going to force pause on the screen. Go ahead and try both of these. When you're ready to check your answer, hit continue. All right, answers are on the screen. We should have gotten negative ln of 3/5, which is 0.511, and 2 for the other one. So if you need to change any of those, go ahead and pause your screen now. All right, so for exponential models, we're often going to be looking at this kind of as our parent function. So can you go ahead and put y equals a e to the bx in your notes? Okay, and if we're talking about exponential growth, then we mean that typically b is negative but a is positive. So I'm going to put a greater than 0. I'm sorry, the a and b are both positive for exponential growth. For decay, while a is positive, b is going to be negative. Okay, and our first goal is to find a and b for our particular problem because x and y are variables, and so y is dependent on x. All right, go ahead and write this for a. A is your initial amount. So that's what y is when x is 0. Oftentimes x, your independent variable, stands for your time, okay? So a is how much you have in the beginning, your initial amount. So that would be, in this case, your y-intercept. B is your rate of growth or decay, okay? So go ahead and put those in your notes, and then let's try an example. Force a pause on your screen. You don't have to write all of this, but will you please put in your notes the 3 pieces I have underlined? All right, so we want to find the exponential model y equals a e to the bx that goes through these given points. All right, so what this means is we want to know what is a and what is b. That's what this means by find the exponential model. It means find a function, okay? So I would still have y and x. Those are my variables, but I need to figure out a and b. All right, so let's start just by plugging in 0 for x and 1/2 for y. So I've got 1/2 equals a e to the b times 0. Well, b times 0 is 0, and e to the 0 is 1. So I have 1/2 equals a times 1, which is just a. And this should make sense because we said that a was what? A was our initial amount, which is what y is when x is 0. So now I've got a. Now we just need to go find b. So let's plug in the ordered pair 4, 5 next into this equation. So I've got 5 equals, I know what a is now, a is 1/2. E, b is what I'm looking for, and when y is 5, x is 4. All right, so I'm trying to solve for b, so what would you do next? We need to get rid of this 1/2, so let's multiply both sides by 2. So I've got 10 equals e to the b times 4, which is the same as 4 times b. All right, what do we do next? Let's take ln of both sides. So I'll have ln of 10 equals, when I take ln of this side, I just get 4b. And so b is going to be ln of 10 divided by 4. And if I put that in the calculator, I'm getting about 0.576. So my final answer, the exponential model, is y equals 1/2 e to the 0.576 x. Now, is this model representing exponential growth or decay? This is exponential growth because b and a are both positive. All right, now note that your base does not have to be e, okay? It could be any positive number. That's not 1, okay? So here's what I'd like for you to do. Go ahead and write just the words example 2 in your notes. And we're going to take a look at this example. It says the population of a city in 2019 is 28,900. it decreases at a rate of 2% every year. Estimate the year when the population is 2,000, okay? So here's, go ahead and write this. We are going to let X be the year after 2019, and Y is going to be the population. Okay, so I know that I have what ordered pair? I have the ordered pair 0, 28,900, right? Because X is the year, how many years after 2019, and Y is the population, and those are dependent on one another, okay? The population is dependent on the year. Now, we decrease at a rate of 2% every year. So, for decreasing at 2% every year, what percentage of the population do we have every year? We have 98%, right? So here's how we're going to write our formula. Our population equals our initial amount, 28,900, and instead of E as my base, I'm going to have this base of 98%, so 0.98. So every year I get to keep only 98%, okay? And then X is going to be the number of years past 2019, because again, every year I just get to keep the 98%. Okay, so now we are going to plug in 20,000 for X or for Y. That's a population, and I want to know the year, so we're plugging in 20,000 for Y. And we want to solve for X. I'm going to force a pause on the screen, see if you can get X on your own, and then hit continue when you're ready to check your answer. All right, so a couple ways to go. The fastest route is probably to take log base 0.98 of both sides to get rid of the exponential here. So this just becomes X then, and then what I do to one side I have to do to the other, so I'll have log base 0.98 of all of this. And if you put this in the calculator, it is about 18, okay? So about 18 years after 2019 is going to be 2037 is when this city is only going to have 20,000 people. All right, so one of the most common applications for exponential growth is compound interest. Compound interest is interest computed on your original investment as well as any accumulated interest, okay? And interest is money you make by putting your money into some kind of like savings account, and so the bank is going to give you a percentage for keeping your money with them, essentially, okay? So that's extra money earned by letting your money sit in the bank's account, okay? Now, the letters we use are P for principal, R for rate, and A for amount, okay? So I'm force pause on your screen. I'd like for you to write those pieces. Okay, so those are the letters we are going to use. Get this bigger. All right, so you didn't need to write this table down, but let's talk about how much my money is going to be worth after a certain number of years. So after 0 years, all I have is what I put in, which is the principal, right? However, after 1 year, we are going to have the principal plus whatever my interest rate is on that principal. So like if I make 1%, I'm going to take my principal times 0.01 and then also, of course, add what I originally had. So what I originally had plus what I'm making in interest. And another way to think of this, if I factor out that P, it would be P times the quantity 1 plus R. Okay, now as we go on, my second year, I'm going to have what I had my first year, which is P times 1 plus R, but then I'm going to make interest on that. So I take that and I multiply it times 1, because I keep it, plus my interest rate, okay? So in other words, I've got P plus 1, P times 1 plus R, that quantity, squared, right? My third year, I get to take all of that, but then I'm going to make interest on it. So I get to take what I have plus my interest rate, giving me P times the quantity 1 plus R cubed, okay? And we can continue this pattern, right? The fourth year, I'll have p times the quantity 1 plus r to the fourth. In general, then, for t equals however many years, I'll have p times the quantity 1 plus r, where r is my interest rate as a decimal, to however many years time t. All right, so here's my formula. Don't write it quite yet, because oftentimes the bank will say, well, we'll compound your money k times a year. So if we're going to compound it monthly, we are going to compound your interest, your money, 12 times a year, right? So instead of just multiplying by t, I get to multiply by t times k, right? Or k times t. But I don't just get that percentage every single time. That would be a whole lot more money. What they're going to do is take my rate and divide by that number as well. So let's say my interest rate is 12% and we're compounding once a month. So I don't get that 12% 12 times a year, but what I do is I get 1% in January, and then I get another percent in February, and then I get another percent in March. And the reason why this is better than just waiting until the end of the year to get all that 12% is that, remember, we get to keep making money on everything that's in our bank account, including that interest we've already earned. So the more times we compound, the better it is for us, the more money we're going to make in the long run. So when we are choosing bank accounts, we want to not just look at the interest rate being offered, but also how often it's being compounded. So force pause on your screen, make sure you've got that equation, and then we're going to look at example 3 together. All right, so for example 3, it says a sum of $10,000 is invested in a fund where interest is 8%, compounded semi-annually. Find the amount of money in the account after 5 years. Okay, and in your equation, let's also add A equals for amount. So our amount is equal to this. So let's make sure we know what all our letters are. We want to know the amount, so we're looking for A. So we need to make sure we've got all our other constants and variables figured out, okay? So 10,000, what letter does that go with? That goes with your P. That's your principal, how much you initially invested. What is R? R is 0.08. Make sure you take your rate and put it into a decimal. So 8% is 0.08. What is K? K is 2 for semi-annually, so that's twice a year. And what is our T in this case? T is 5. Okay, so now I'm gonna have you first pause on your screen. Go ahead and set up our equation. So here's how I set it up. Plugging it into the calculator and rounding to the nearest cent, I get $14,802.44. So in just a matter of 5 years, we made almost $5,000 just by letting our money sit in this account. 8% is a great interest rate. That kind of interest rate is not feasible right now, but it's not historically unknown. Like, we have seen interest rates that high before. Now, I do want to point out that this is all dependent on several things, right? In addition to how long your money is there, as well as your rate, the initial value played a big role here, right? Our principal. So this is partially where the saying comes, it takes money to make money. The more money we had here, the larger our final answer would have been. All right, so we've got this idea of compounding, right? In that previous example, we compounded semi-annually. We might compound quarterly, so 4 times a year, or monthly, so 12 times a year. But there is such a thing as continuous compounding, which is compounding every single moment, which is obviously the best kind. So what this means is, what happens when you let K, right, because that's how many times we compound a year, increase without bound. In other words, what happens when you take the limit as K approaches infinity? Well, we're going to test it here. We're going to take our usual formula, A equals P times 1 plus R over K, all to the KT, or make the substitution that we're going to let this letter N equals K over R. Well, if N equals K over R, notice that as K goes to infinity, as K gets larger and larger, n is going to approach infinity as well. Okay, now I'm going to manipulate this algebraically a little bit. I can flip both sides. So if I flip the left side, I get that 1 over n is equal to the right side flipped, which is r over k. All right, I'm going to also take this and multiply both sides by r, so I'd get n times r equals k. All right, so why is she doing all this? Well, let's now take this formula and make some substitutions. So I still have a, I still have equals p times 1 plus, now I'm going to make the substitution r over k equals 1 over n. So I have 1 over n here. And then I have that k is equal to n over r. So I'm going to replace this k, not n over r, n with n times r, and I still have that t. Okay. Does this piece look familiar at all? Do we remember seeing this quantity? We used x instead of n. But we at one point looked at the limit as x approaches infinity of 1 plus 1 over n all over n. Let's pull it up. All right, so here's that expression, 1 over 1 plus n all to the n, but I'm using x. As x goes to infinity, do we remember, you can see that we've got a horizontal asymptote there, right? You can see, okay, getting closer and closer to some number. Do we remember what that asymptote is? So y equals e, right? This is our special Euler's number e. So coming back to what we were writing, I can replace that boxed part with what number? E. So my final answer is a equals p times e, which is close to what integer? 3, to the r times t. Okay, p, r, and t all still mean the same thing, but if it's compounded continuously, I basically get to replace this piece with e, the number e. First pause on your screen. Let's make sure that we've got both those formulas in our notes. And hit continue when you are ready to do one last example. All right, example 4, it says you invest $300 in a bank account that compounds interest continually. So as soon as I see that phrase, I know I get to use a equals p e to the rt, PERT, okay? 10 years later, you have a total of a whopping $385.21, okay? What was the interest rate? All right, so let's figure out our letters here. So remember that your variables are a and t. So a depends on time. My amount in the account depends on the time in the account. All right, so 300 is what? 300 is p. What is 10? 10 is t. And I'm looking for r, right? So where do I plug in this? I plug that in for my amount. That's what my amount is when time is 10. So I'm plugging in 385.21 for A, and then we're going to solve for R. So I'm going to let you plug that in. Go ahead and solve for R and hit continue when you are ready to check your answer. All right, I've got the answer on the screen. Go ahead and pause if you need to correct anything. We should have gotten ln of 385.21 over 300. All of that over 10. If we plug this into the calculator, we get about 0.025. So making that an actual rate, a percentage, move your decimal over 2 places. This will be a rate of 2.5%. All right, you all, that is all I have for today. I will see you next time.